Hello everyone, my name is Jay Castro and this is my CS131 fall semester project. I decided to do my research slash presentation on what I believe is one of the most intriguing uses of AI, Google's DeepMind AlphaFold AI. The reason I believe it the most exceptional is that it has been used to solve one of biology's biggest challenges, predicting how proteins fold in their three-dimensional shapes. We'll look at why this problem was so difficult to begin with, how AI has sort of cracked the code, and afterwards show a visual demonstration of the proteins by using a couple Python libraries I found online. So what's on the menu? First, I'll go over what is a protein. Second, the protein folding problem. Third, why traditional methods have failed. Fourth, I'll introduce AlphaFold, the quote-unquote AI solution. Fifth, I'll do a slight code demonstration, really just showing how these predictions have been uploaded and are readily available for anybody who would like to access them. And lastly, I'll talk about the impact and recognition that AlphaFold has received. What are proteins? Let's start with the basics. Proteins are just chains of amino acids. I like to think of them like discrete units or building blocks in a sequence. There are 20 different standard types of amino acids, and the sequences of these amino acids determine the protein's chemical properties. But here's the cool part. Proteins don't simply stay as a straight chain. They fold into specific three-dimensional shapes, and these shapes determine how the protein interacts with other molecules in the body. These shapes aren't simple, I would say, like DNA or RNA. These shapes often intertwine, form many loops, and can often be seen on social media, such as the engine that walks. These proteins form such complicated shapes that there's just a vast amount of possibilities for each one. The issue is when proteins misfold or when we simply have no idea what 3D shape these proteins form at the end. When a protein misfolds, it can cause serious diseases such as Alzheimer's, Parkinson's, or cystic fibrosis. So having accurate models of how proteins fold is critical for understanding biology and medicine. Now I'll go over the protein folding problem. So the problem is this. Let's say I'm given a sequence of amino acids, which is really just a series of letters in a text file or in a certain format. And from this just linear line of letters, which are amino acids and mean things to biologists, can we predict the exact 3D structure that this little line of amino acids will form? It's a little simpler when doing it with DNA or RNA because we know that these are going to be in a general shape, but we really don't know that with a lot of these proteins. So now, doing this by hand, it is an incredibly difficult and tedious task that is time consuming. Biologists need to know the precise coordinates for every atom and which atoms are closest to each other in space in order to get the final shape. This is called the process of protein crystallization. Unlike DNA, which is more predictable, protein structures have an outstanding amount of possible structures. Why have traditional methods failed, / why is it so hard? Well, here's the gist of it. The answer is combinatorial explosion. Each amino acid in the chain can exist in multiple different orientations. And to simplify the problem, let's say there are only like 10 positions the amino acids can be oriented in. For a protein with 100 amino acids, that means roughly 10 to the 100th possible structures. That's a whole Google. A 1 followed by 100 zeros. And now, me personally, after learning this, I wondered how scientists were able to predict any protein structure at all before using AlphaFold. And that's when I learned that we can't brute force our way to a solution. Even with quantum computers, this is practically as difficult as some cryptographic challenges that have been presented. So in 1969, a scientist named Cyrus Leventhal calculated that if a protein tried to find its correct shape by randomly testing possibilities, it would take longer than the age of the universe. Yet in living cells, proteins fold correctly in milliseconds. This is called Leventhal's paradox, and it shows that proteins can't be predicted using random search. Brute forcing is clearly not the answer. We cannot guess, and we cannot iterate through millions of different possibilities because there is more than that. There must be a pattern that we can exploit computationally. That's where AlphaFold enters the scene. AlphaFold changed everything. AlphaFold is an artificial intelligence system developed by Google DeepMind. Instead of trying to search all possible structures through traditional methods, through guessing or brute forcing, AlphaFold learns to predict the structure directly. It's a deep neural network similar to the LLMs or face recognition libraries such as DeepFace. In fact, DeepMind trained AlphaFold on over 200,000 known protein structures from the protein data bank, teaching it to recognize patterns in how sequences fold and interact with each other. When you give AlphaFold a new protein sequence, it doesn't search it at all. It simply predicts the structure based on what it has learned previously. It does this in seconds and minutes at slowest, compared to the previous standard, which was years of focus, research amongst multiple laboratories. In 2020, AlphaFold participated in the CASP-14, a competition where scientists attempt to predict protein structures that have been experimentally determined but not yet published. AlphaFold scored 244 points, with only 98 points being scored by the next group. Such a remarkable performance led to people wondering if the protein folding problem was finally solved once and for all. Now I'll give a high-level, simplified overview on how AlphaFold works. It is honestly beyond me and beyond many other researchers. Here's how AlphaFold works at the high level. You start by giving it an amino acid sequence. AlphaFold first creates what's called a multiple sequence alignment, which means it looks at similar proteins across different species to find evolutionary patterns. These are amino acids that change together, most likely interact with each other. Then it runs through a neural network using transformer architecture, which is the same type of tech that powers a lot of LLMs such as ChatGPT. The network predicts distances between every pair of amino acids, essentially saying these two amino acids will be close in 3D space, while these two will be much further apart. Then a structure module refines these predictions into actual 3D coordinates. These 3D coordinates are then published and are what I use for the coding demonstration, which is next. The key innovation in use of attention mechanisms which allow the network to learn which parts of the protein interact with each other. AlphaFold learned all of this by studying over 200,000 existing protein structures, recognizing patterns in which similar sequences fold, and understanding the physical and evolutionary constraints on protein structures. Now, for the coding demonstration. So what exactly will we be looking at? Well, what the code does is it downloads a hard-coded insulin protein prediction that the AlphaFold AI already made. It is readily available through the AlphaFold API to the public. No need to make an account. The 3D coordinates are then parsed from the file. The 3D structure is then visualized using the 3D mol library. And colors are red and blue for the different confidence levels that the AlphaFold AI had when making this prediction. As you can see here, there are varying levels of accuracy and confidence in what the structure will look like. And from all the structures that I was able to test with, it seems that the closer they are to the center, to their core, the higher accuracy they have. Now, some closing remarks regarding the impact and recognition of AlphaFold. So, the impact of AlphaFold has been enormous. In terms of accuracy, about 90% of AlphaFold's predictions match experimental structures, meaning it's comparable to doing actual experiments in many cases, but that's not completely trustworthy. It is still worth, oh my god, that's terrible. This cap. In terms of scale. Okay. Now, a couple words. Now, some closing remarks regarding impact and recognition of AlphaFold. The impact of AlphaFold has been enormous. In terms of accuracy, about 90% of AlphaFold's predictions match experimental structures, meaning it's comparable to actually doing the experiments in many cases. This is a revolutionary improvement over previous computational methods. In terms of scale, AlphaFold has predicted over 200 million protein structures. That's essentially all known proteins across all organisms, and all of this is freely available to researchers worldwide through AlphaFold's database. The recognition has been significant too. In 2024, Demis Hassabis and John Jumper from DeepMind were awarded the Nobel Prize in Chemistry for their work, cementing AlphaFold's place as a solution to a 50-year-old grand computational challenge. Now, in terms of real-world applications, AlphaFold is being used for a multitude of ventures: drug discovery to identify where drugs can bind to proteins, indices research to understand how misfolded proteins cause conditions like Alzheimer's, and enzymes engineering to design new industrial catalysts, and across structural biology to accelerate research that would have otherwise taken years using traditional methods. My personal thoughts on AlphaFold is that this is where AI needs to go. This is where the money should be. And I really hope that we get more useful AI tools and models that can help make the world a better place. Thank you so much, and I hope you enjoyed. Welcome to my channel.